In Lab 5, we experimented with Faraday's law by creating a solenoid-like parcel to drop a bar magnet through. In this report, I'm going to introduce the problem, talk through the procedure, show the code, and ask and answer some additional physics questions. The problem that we were solving is how long a bar magnet takes to fall through a solenoid and why it does not just free fall. A solenoid consists of multiple connected loops of metal or wire, similar to a coil. The key difference is that the length of the loops is larger than the coil's radius. The solenoid acquired an induced current when a bar magnet was dropped through it. Faraday's law is a law of magnetism that says how a magnetic field will interact and produce an induced current. The current can be induced due to a changing magnetic field. Lenz's law states that nature abhors change, so the induced current will try to balance out the change in magnetic field. A roll of aluminum foil acted as a solenoid in this experiment. It was very important to make sure there was at least 1 centimeter of foil on the roll, so the current could be induced. We also had a bar magnet given to us by the instructor, a meter stick, and a device with a Tesla meter application. The device was used in finding the north and south ends of the bar magnet. The bar magnet acted as a dipole, which had a magnetic field that was changing while it was moving when it was dropped through the solenoid. There was then an induced current in the solenoid trying to balance out the changes in the magnetic field that were occurring when it was falling. We timed the magnet falling through the solenoid and took the average of 5 trials. We used the meter stick to measure the width of the aluminum coils and the length of the roll as a measure of the solenoid's properties. We then solved for the magnetic dipole moment, mu, which we also previously did in the last lab. We measured the magnetic field B with a Tesla meter application and R with the meter stick, and then solved for mu using the formula below. We created a glow script code using the length of the roll, the inner radius of the roll, and the width of the foil on the roll, and plugged it into a previously provided to us code. We created the bar magnet and defined a function for finding the magnetic field. We then graphed velocity versus time for the falling bar magnet, which looks like this. The plot is not linear because the magnet is accelerating due to gravity, so the magnitude of the gravitational force is changing. Only constant forces create a linear plot. In the graph, the velocity is constant throughout the tube, as you can see by the straight line. It then accelerates due to gravity before and after entering, when the gravitational force is dominating and increasing. The time that the computational model took was 1.334 seconds in the tube, but the real-world model was 1.94 seconds in the tube. The differences are caused by inaccuracies in the computational model that could be fixed. Air resistance was not taken into account in the computational model, which slows the magnet down more, as can be seen by the real-world model being longer. The angle by which the magnet was dropped can also affect the magnitude of the flux, and this can be added in the code. The tube in the code is colored, and the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Red corresponds to counterclockwise current and blue to clockwise. I know this because the magnet spins in the direction opposing the change in the magnetic field. If you were to flip the magnet around, the colors would actually flip because the induced field would be pointing in the opposite direction than before, because the change in magnetic flux would then be in the opposite direction. If the resistivity in the conductor were reduced to as close as possible to 0, the dynamics of the falling magnet would change by causing the conductivity to increase, and then more current would be yielded. This is because by Ohm's law, V equals IR, so I equals V over R, and since R is smaller and the voltage is the same, it will cause I to be larger. If holes were cut into the tube, this would affect the ring currents by causing the magnet to almost free fall. In conclusion, this was definitely the most interesting lab by far. I really liked how we could see the effect of Faraday's and Lenz's law in action. It was amazing how the solenoid could be replaced by a household item such as a roll of aluminum foil, and cool to see Physics 2212 in action one last time.